Hello, everyone, and welcome to today's session of Faster Analytics on Cloud with RubiX. Before we get into the presentation, let me introduce myself. My name is Shubham, and I have been working with Qubole engineering for about 7 years now. During this time, I have worked on development of a couple of big data engines like Presto, Hive, and Hadoop, and I've come across multiple other big data engines. And all this while, across all these engines, the topic of speeding up data storage layer has been a point of interest. And that is how RubiX came into being. And that's what we are going to cover today in our presentation. Right, so the agenda is as follows. Because we're talking about speeding up of data storage layer, we're going to look at the lay of the land about big data storage, where it started, where is it right now, why is it where it is, what are the problems with it, and how RubiX fits into all of this. Then we'll go into the RubiX overview. We'll discuss what RubiX does, how does it do it, why should you use it, and how can you use it. Then we'll go into the availability section of RubiX. If you want to use it, where all is it available? We'll show you some of the ways you could easily enable RubiX in certain engines. And if you do not have native support, how can you get started with it? Then we'll go into the most interesting part of the slide, which everyone I'm sure would be waiting for, which is around the gains, the performance gains, and the impact of RubiX on cost. We will look at data across multiple clouds, and we'll cover both performance and cost in that section. Towards the end, we will finish up with the features that have been recently added to RubiX and the features that are coming up in a few months' time. So big data storage, as all of you would definitely know, when big data started, probably around a decade ago or so, it started with Hadoop. And it was natively built for data processing, with data residing in the same data center where your processing power is, right? So you would have, big companies would have their own data centers, or they would be leasing some data center, but your compute and storage would be all together. Your disks would be a huge rack of storage and will be directly accessible to your processing system. That worked out great for a long time, but slowly cloud came into being, and there was a transition from your own data centers to cloud. Even during this transition, a lot of deployments, how they look like was that you'll have all your processing and storage bundled together on the same VMs on the cloud. The most prominent example of this is accessing data over HDFS, right? With Hadoop, you have your Hadoop MapReduce tasks running and all your HDFS data located within same clusters. But slowly and slowly, big data stores came into being. And over time, they became the de facto standard for building your data lakes. So data stores like Amazon S3, Google Cloud Storage, and Azure, Microsoft Azure's Blob Storage are now the place to go to if you're building your data lakes. And these became de facto standards for some good reasons. And I'm listing out a few of those reasons here. You get infinite scale with these cloud stores. You do not have to worry about procuring disks, adding them to your racks, and only then having them available for your usage. You have infinite scale at your disposal. Whenever you want, you can increase your usage of disk space. You don't have to worry about any of these operational stuff. All of this is managed storage. Gone are the days where you have to worry about loss of data on the disks, right? Setting up disks. Everything is managed for you. It's pay as you go. Whatever you use, you pay for that data, and it's completely managed by these cloud providers. And all of this is shared access. So again, it minimizes the impact on operational requirements. You do not have to worry about setting up disks such that it's available across all the nodes. You don't have to worry about network storages and different protocols around that. It's all available in the cloud and all accessible completely to all of the nodes that you may have for your computing. One major benefit, which has been instrumental in this movement of data stores to be the place for data lake, is decoupling your storage from compute. Traditionally, we have seen that a lot of warehouses have had problems with very coupled infrastructure of storage and compute. So whenever there is a requirement to scale out storage, they will have to scale out the compute as well. even if they do not need compute for all that storage. Let's say they have storage for 10 years, they do not need compute over all the 10 years, but because everything is coupled, they have to scale out accordingly. What cloud stores bring is that now you can scale out your compute and your storage independently. This brings down the costs of your overall infrastructure tremendously. The next point is about the cost, which is a very important point, and I have mentioned a star mark here, which we'll cover in the next slide as well. But generally speaking, the cost, the dollars per gigabyte, coupled with all the costs of not managing the storage at all, makes the whole setup of cloud stores really inexpensive. Finally, the ease of use. If you look at today's ecosystem, big data ecosystem, every engine supports cloud stores out of the box. You do not have to worry about doing any plugins for this. In fact, these days, all the engines have such a great support for these big data stores that there are optimizations in place so that these engines work well. They leverage the best performance out of it because there are certain access patterns which work well with cloud stores, some don't. So engines try to optimize for all of this, and users do not have to worry about it. It just comes in pre-packaged with all of these engines. So there are a lot of great things which has led the industry to move towards cloud stores. But of course, there are always some problems lurking here and there, and I'm going to cover a few here. The first one about network latencies. It's pretty evident, right? If you are talking about a network store, which you might be accessing over intranet or internet, there are a lot of hops involved in between. Because there are so many hops, there are going to be network latencies. Of course, the latencies will vary depending on from where are you accessing, how far off you are from these cloud stores, but they'll always be there. The second point, which is in a way related to network latencies, is inconsistent performance. If you are running your workloads in cloud, I'm sure you would have noticed that same workload across different points in time will have variations in performance. Right? One part could be attributed to network latencies because there are latencies and latencies are not consistent. So the performance is going to be inconsistent. Small inconsistencies in performance is fine. But we have seen that with cloud stores, there are times when there is substantial degradation in performance. And that part could be attributed to the throttling feature of these cloud stores. So most of these cloud stores, well, all of these cloud stores are services. And just as a defensive mechanism to prevent themselves from some unruly hosts, they have to have preventive mechanisms to throttle these hosts from sending too many requests, right? And this just depends. It might your workload might be such that you require that high rate of requests, but because your cloud providers deems your machine to be fitting into the category of throttling, it will throttle you back, and that will lead to inconsistent performance of your workloads. The third point is about costs, and this is the star mark which I had pointed in the previous section. Though generally speaking, your cloud stores are inexpensive, but if you are correctly using them, so there are some places where if you are not careful, you will incur some unexpected costs. One example for this is if you are accessing, I'm taking example of S3 here. If you are accessing S3 across regions, so if your S3 bucket is in, let's say, US East and your compute is in Asia Pacific. So these are two different regions, and when you are accessing data across regions, there will be additional costs incurred. And here we're talking about big data, so there will be a lot of data transfers between S3 and your compute resources. So the amount that you will see on your bill attributing to this inter-region data transfer cost is going to be substantial. So these are a few of the problems. And looking at the problems, I'm sure that it will be popping up to you that data caching seems to be the solution to all of this. It completely makes sense because with newer machines, all machines in all the clouds these days supports SSDs, right? And those SSDs can be used to cache this data, the most frequently used data, close to your compute resources. And RubiX is one such system that is used for data caching in Qubole. As I was saying that during our journey with all of these big data engines that we support, we had also seen a requirement of having the system. And So we built RubiX about in 2016, 2017, and since then, RubiX has been the data caching layer for all the big data engines in Qubole. Okay, quickly going through some of the key points about RubiX. We already covered what it is, right? It's a caching framework, and it's not just the big data engines that Qubole supports. Any big data engine that tries to access storage over a Hadoop-like file system layer, RubiX can be used for data caching there. And RubiX follows and tries to follow a keep it simple architecture. It doesn't try to do fancy things. It tries to delegate whenever it can delegate certain parts of the functionality to the systems which it knows can do things better than it. For example, one example for this is that it doesn't try to do in-memory storage. It tries to keep everything on disk, on SSDs. And it tries to leverage the operating system's page cache. Operating system page cache is super mature. It's been there for ages now. So page cache, it relies heavily on page cache to do the right thing and cache the memory data in memory, which is quite frequently used. Other than that, there are other aspects to it as well. Though RubiX is a multi-node service, that is that on each of your compute node, you will have RubiX servers running. But all of these servers are quite independent of each other. They work in cooperation with each other. They talk to each other. They may read data from different servers running on different nodes, but they're very independent. There is no central entity like a coordinator worker kind of mechanism. There is no central entity governing your RubiX servers. That gives you a very important benefit that there is no central registry. We have seen in past that systems like HDFS, which have a central registry of what file, what block resides where in the cluster, in a highly scale out sort of a system, that really falls apart because there is a lot of pressure on the central registry. And RubiX tries to keep the architecture simple, let each of these RubiX server which are running on different machines work independently, figure out whatever they need to figure out independently, do not go to a central machine, which works out really well in a highly scale out architecture. It is highly pluggable. And there are two aspects of pluggability here. One aspect is about pluggability into big data engines. You could extend it to any big data engine, as I already mentioned in the first point. So Presto, Hadoop, Hive, Spark are already supported. And the other aspect is supporting different cloud stores. So any cloud store can be easily plugged in. AWS, GCP, and Azure are already supported. And it's very easy to plug in if there is a new data store tomorrow. You can very easily plug in with writing just one file, and you'll get data caching over that cloud store as well. Next point is about friendliness to columnar supports. We know columnar support is very important with all these big data query engines, which means that you read only the amount of data that you want to read. If you're reading one column out of 100 columns, these engines will only read data related to that column. And RubiX also works well with that architecture. It is only going to cache the data that is being read and only cache the data that is being read. So as an outcome, it's going to work really well with the columnar data format, because if you're reading one column out of 100 columns in your data, RubiX is going to cache your data for only that column. Finally, the point about ease of use, it's very simple because the architecture is simple, the deployment is simple. You just have to bring up service and it's completely transparent to your end users. Admins just have to bring up RubiX servers and just enable some config in your big data system, and you're done with it. Your end users do not have to do anything like changing your schema or changing some locations and anything of that sort. It just works out transparently for them. There's another point about ease of use, which we will cover in a short while, which further simplifies this deployment model, which is almost like a one-click model. You don't have to even worry about the operational stuff of bringing up servers. You just have to enable RubiX and you're good to go. And that's one point which we're going to cover in one of the upcoming slides. So availability, I already mentioned it's available, it's pluggable, and already supports a lot of the big data engines which are common right now. But there are certain engines which provide out-of-the-box integrations for RubiX. That means that you don't have to worry about setting things up. It's almost like a one-click solution. On Qubole, RubiX anyways is the native solution. So big data engines like Presto and Spark on Qubole support this out of the box. We'll see how you can enable it. Presto SQL has an out-of-box integration with RubiX. This came out interestingly last year when we had a Presto summit here in Bangalore, and Presto founders came down and the discussion about RubiX came in. And they were interested to integrate RubiX because it's going to be a very simple caching solution for the end users. So that's how the work started. And now we have natively inbuilt support for RubiX in open source Presto SQL. Finally, HT Insights IO Cache is also powered by RubiX. If you are using some other engine or some other provider which doesn't provide out-of-the-box integration with RubiX, there is always an option to manually install it. There is a tool called RubiX Admin, and that could easily install it over any of your existing cluster. There are blogs out there how people have integrated this over EMR, and custom deployments of RubiX are easily possible over AWS, GCP, or Azure, or whatever cloud you use for that matter. All right, how do you use it? In Qubole, it's very simple. When you go edit your cluster, so this is a snapshot of a cluster edit page inside Qubole UI. So if you go and edit your Presto or a Spark cluster, in your advanced settings, you will see a checkbox of enable RubiX. You just have to click that, and that is all. You do not, this one click is going to set up RubiX servers for you, do the required configuration changes for you in these engines, and from the very first query, you will be able to utilize the power of RubiX. In Presto SQL, there's a different mode, which I talked about briefly, the native mode. And here also the configuration is very simple. Inside your Hive Hadoop 2 connector, you just enable caching, right? And you just pointed out that what location should RubiX use for cache, and that's all. Post this, once you start using your Presto SQL cluster, you will be leveraging RubiX there. All right, so the most interesting part of the presentation, gains, performance gains, and of course cost gains as well. Before we get into numbers, I just want to talk about two things, IO boundedness and CPU boundedness of your workload. Your workload could be IO bound if it is actually being slowed down by IO, or and in that case, speeding up your storage layer will immensely benefit from the perspective of performance. On the other hand, there are CPU bound workloads which are heavily bounded on CPU. In these cases, even if you improve the performance of your storage layer, you are not going to get a lot of improvement in performance. But for the completeness sake, I'm covering all type of workloads here. And just to mimic these workloads, I have used TPCDS in both of these cases. To mimic IO boundedness, what I've done is that I have kept my bucket in a different region in S3, and my compute is on completely different region. So the transfer of data is almost over internet, right? So that is slower. So your workloads, same TPCDS workloads are going to be IO bound. For CPU bound, I have kept the bucket in the same region. And if the data is close to your compute, TPCDS is usually CPU bound. If you go track your CPU usages, TPCDS is going to keep your CPU usage pegged at more than 90% most of the time. And all of these numbers are with Presto SQL 317. All right, so getting into numbers. For IO bounded workload, we were able to see a maximum of 3x improvement for the workload. And on an average, the TPCDS 100 queries ran 1.7x faster with RubiX in comparison to the case when we were not using RubiX. So these are great gains. And these do not come at any additional cost because whatever machines that you are provisioning are already coming with SSDs. It's just that you are now using those SSDs for data caching. So you can speed up your workloads. If your use case is IO bound, you can speed up. And it could be, again, much higher than 1.7x. And you can get that without any additional costs. Talking about costs, if your workload was IO bound and was following a cross-region pattern, as I showed here, of course, people do not use it. Cross-region is usually handled by people cleverly by doing replication across regions and just incurring the cost once and reading the data over the local region. But in a big setups and big enterprises, there are always situations where it's very hard to keep track of everything, and you might end up having some leakages here and there, which could end up in high costs. And this is one example of the cost here. The TPCDS run that I did here for cross region costed me around $28 for just in S3 cost, because I was transferring data across region. With RubiX, it was just 1/3 of it, around $9, because I was just reading data once. Right? Getting into CPU bound workloads, and here I have some graphs for all the clouds. We see varying improvements across AWS, GCP, and Azure. And if you compare AWS, you'll see that the maximum benefit has come down from 3x to 2x. But there are, nevertheless, there are benefits. And over Azure, we could see some queries had gone in and had almost 5x sort of improvements. So across both the types of workloads, we see that there is definitely a scope of improvement in terms of performance and in certain cases in terms of cost. Okay, so quickly, I'm going to go through the recent improvements that have been done. Our community has been really active in the past 6 months or so on RubiX. We have been getting traction from committers, contributors outside of Qubole as well. And this embedded mode is the one which I was talking about. It's a new mode that got added in RubiX, which just simplifies your operational complexity to a single click. This is what Presto SQL integration has been done with. What this means is that RubiX can now run within your big data system. So your big data system like Presto could spin up RubiX daemons within itself. And that's if you just enable RubiX, and you don't have to worry about enabling it yourself. So yeah, this is one major step towards the ease of use. GCP support was recently added, and the numbers I had shown you is using that support. There is improved handling of membership change. This is critical from the angle of autoscaling. If you are using RubiX in a system which autoscales a lot, scales up and down, which means the membership of your cluster changes, we have put in recent changes where we have improved the core logic of consistent hashing, which helps in bringing down the impact of this membership change by minimizing the redistributions that are done across the nodes. So this is one major improvement you should look out for if you're using systems in an auto-scaling ecosystem. From performance angles, we have added connection pools. Presto is again, RubiX is again a collection of servers, and these servers communicate with each other over network. And to improve performance and of course reliability, we have added logic of pulling these connections. There are improved invalidations. Invalidations will happen when either you're running out of disk space, RubiX will do invalidations, or RubiX figures out that a file has changed on the actual source, so there will be invalidations. And the invalidations are now robust, and it is guaranteed that whenever there is a change in your cloud store data, there will be invalidations on RubiX side. Another important point is about warm-up. We have improved the warm-up of RubiX. RubiX used to traditionally support synchronous warm-up where the query which is reading the data is going to be directly impacted by RubiX warm-up because within the lifecycle of that query itself, we are going to synchronously bring in the data to cache. So the overall time of query is going to increase a lot. Over time, we had added a parallel warm-up or asynchronous warm-up where the query is not really impacted a lot by warm-up. Whenever a query comes in for data that does not exist in cache right now, there is a request which is registered, and these requests are asynchronously handled by a different server. So the cost of warming up your cache is not paid by the queries that are reading data. And this asynchronous mode of warm-ups is now default in RubiX. Finally, we have improved statistics a lot in RubiX. So if you want to drill down, get details about your cache usage, etc., you will see a more detailed and much better statistics in RubiX now. All right, quickly going through the few improvements that we are planning to bring in. We are planning to bring in metadata caching. So this is about listings cache in RubiX. This is from an angle to save some costs. Again, taking example of S3 here, apart from data transfer costs, S3 also has costs on API calls like listings and get calls. Of course, get calls are handled already, but listing calls could be handled by your metadata caching. Then there is an improvement. This is an improvement we plan to take up within RubiX. We want to minimize the amount of listings. This is directly related to one because it's going to save on the listings cost. So we want to minimize the amount of listings that are done in RubiX, which is right now done in order to figure out if invalidations need to be done, data has changed on your cloud store or not. We want to minimize how many listings we do in RubiX. One feature that we plan to do is pin to disk, where you could, if you have certain locations which are more important than others, then you would want to pin them to disk and say, even if there is a crunch of disk space, never evict this. Always evict some other locations in favor of these locations because these are more important to my workloads. Finally, we want to add a table level administration. So RubiX is a construct over file systems, but most of its usage is over query engines. So adding a table level interface on top of the administration layer of RubiX will help the admins a lot. An example for this could be that the pin to disk feature that I talked about, where you would want to give locations that you would want to always pin to disk. You can talk in terms of table partitions. Instead of saying certain locations are more important, you can say certain partitions of my table. Say last 3 months of partitions of this table are more important, pin them to disks. Right? So that is what I mean by table level administration. That is it. So this was a quick overview of RubiX, and we welcome all the contributions. You can find RubiX source code on Qubole's GitHub account. There is a Slack channel for RubiX you can join if you have any questions. I have shared a documentation link as well. And there is a Google group listed here for the RubiX user. Any questions around using or dev questions around code or anything else for RubiX, questions are always welcome. Thank you.